Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be talking about the area of polar curves. Okay, so we're going to find the area of one polar curve today. We're not going to work with multiple curves, just one today, so that we get the idea of how the formula works and all that jazz. So let's get started on taking a look at how we're going to go about doing this. So, what we're going to be doing is, well, the first thing we have to do is we have to go back and we have to remember that the area of a sector of a circle is the region that's bounded by the two radii and the intercepted arc. Okay, so basically, when we say the sector of a circle, we're talking about maybe a slice of pizza or something like that. You want to be able to find the area of that sector. The formula to find the area of a sector of a circle is 1/2 r squared theta, where theta is the angle here and r is the radius. Okay. And theta has to be in radians. All right. Theta cannot be in degrees. If theta is in degrees, you have to convert it to radians. Okay. That's how you would find the area of a sector. So this is the idea here. All right. This is kind of the formula that we're going to play with. So let's say I had a polar curve and it looked like that. I don't know, just to say it looks like something. All right. And I wanted to find the area of that polar curve. Well, I could find the area of that polar curve. Um, it would be, I guess, fairly difficult to do that. So I need to develop some kind of formula to go ahead and do it with. So what I can do is I can find the area of a certain sector of, let's say, this um, region here. So let's say I found the area of that region here. So I found the area of this sector that's here. Now, again, that's not technically the area of the entire sector, right? I mean, the sector would come from a circle, okay, which I don't exactly have. This region is not circular, all right? So the question is, how would I then find the area of this entire region, right? Because this sector is certainly not the whole area, okay? It's certainly only a piece of it. Well, let's go back to something that you've actually worked with before. Now, we did this in rectangular form. Let's say I gave you a region and I wanted you to find the area that was underneath this curve. Now, back when you first found area, what you started doing was you put rectangles into the picture, right? So you took the area and you broke it up into the area of a bunch of rectangles. You could work with those rectangles from the left. You could work with those rectangles from the right. Whatever it is that you wanted to do. You could work with midpoints. You could work with other shapes like trapezoids. But back at the beginning, you worked strictly with rectangles. Okay? So now again, this area that's here is certainly, for the rectangles, is certainly not the same area, right? That's underneath the curve that's in purple here. But the question is, how did we go about finding that area then? So if you remember back, what we did to get a better approximation was you made the triangle or the rectangles, you made them smaller, right? You just made them small. And the question is, how small did you want to make them? You wanted to make them as small as possible so you could fit as many rectangles in there as possible. You wanted an infinite number of rectangles, right? And if you had that infinite number of rectangles, then we realized that meant you could integrate the function. And then that's where we came up with the area under the curve is the integral, okay, of that function between the two bounds A and B. All right. So you remember working with that hopefully at some point. So this concept is the same concept we're going to apply here. What we're going to do is we're going to create a bunch of sectors for this region. So I'm going to take this region and cut it up into a bunch of sectors. Well, how many sectors would I need to actually find the area that's underneath the curve? Well, I mean, I could do it with a small number if I wanted to, but if I wanted to get a better approximation, I would need more sectors, right? I would need as many sectors as possible. Okay, I would need an infinite number of sectors, right? But again, what does that mean to calculate an infinite number of sectors? Well, if you find the area of an infinite number of sectors, then theoretically, you should be able to integrate. So then to find the area, I should be able to integrate. Well, integrate what? Well, that's the formula for the area of a sector, right? 1/2 r squared theta. And what's changing here each time is theta, right? We're trying to make theta as small as possible. So if I have this region here, okay, you want theta to be as small as possible. When the angle is really small, right? When the angle is really small, you get an approximation that's very close. So to find the area of a sector or the area of a polar region, you're going to integrate 1/2 the integral from alpha to beta for theta. Theta is equal to alpha and beta. So wherever the region starts for an angle, depending on where it stops for that angle, r squared d theta. So the area formula is 1/2 the integral from alpha to beta, r squared d theta, which is actually a pretty easy one for most people to remember, believe it or not, because it kind of has a rhyme to it, right? Beta and theta rhyme, which kind of helps you. Now, you do need to know that theta has to be between alpha and beta. So beta has to be smaller than alpha. Let me write it like that instead, okay? And that's going to be important. You're going to see in just a minute. Theta or alpha has to be smaller than, or equal to. If it's equal to, then there's no area. But alpha has to be smaller than beta. So the angle on the bottom has to be smaller than the angle on the top. Okay? All right. So that's your formula that you're going to work with here. And again, the whole concept comes from the same concept we already know for rectangles, but now we're applying it to the polar coordinate system. All right, so let's take a look. We'll try a couple here real quick. All right, so I want to find the area of one petal of the function or the curve r equals 3 sine 2 theta. Can't call it a function, right? It doesn't pass the vertical line test. All right, so I want to find the area of one of these 4 petals. Now, there's a bunch of ways that you can do this, okay? You need to understand that these petals, they're all symmetric to one another, all right? So what I need to know is I need to know where a petal begins and where a petal stops. Okay, where one of the 4 petals starts and where one of the 4 petals stops. So now, the petal begins and ends there. We agree? Each one of the 4 petals begins here, loops around, and then ends here. All right? So the question is, what is this point? Well, this is the point where r is equal to 0. So I need to figure out where r is equal to 0, or where 0 is equal to 3 sine 2 theta. So if I divide by 3, I get 0 equals sine 2 theta. And now I need to solve 0 is equal to sine 2 theta. Okay, so now to solve this, remember, theta, or 2 theta, means go around the unit circle twice and name me all the places where sine is equal to 0. So 2 theta is going to, where's sine 0? The y-coordinate's 0, right? The y-coordinate is equal to 0 at 0 on the unit circle, at pi, and at 2 pi. And then I keep going around again. I'm going around twice, so that's 3 pi. So I can divide all of these by 2, and then that'll tell me what theta is equal to. So theta is equal to 0, pi over 2, pi, and 3 pi over 2. All right, this is called solving a trig equation. If you don't remember how to solve a trig equation, go back, look at the pre-calc playlist in trig in Unit 5, and you can find 2 videos on solving trig equations. Okay, so these are the 4 values of r, theta, for which r is equal to 0. Now, the question is, how would I find the area of one petal? So to find the area of one petal, there are multiple ways to do this, and that's what I want you to understand. This is not a one-step deal. This is it. There's multiple ways to come up with the answer. So what I could do, the easiest way to do it is to find the area of this first petal here, which I could do pretty easy. If I start at r equals 0 and stop at, or theta equals 0, and stop at theta equals pi over 2, I could find the area by taking 1/2 the integral from alpha to beta r squared d theta. So that would be 1/2 the integral from 0 to pi over 2, 3 sine 2 theta squared d theta. That would be one way to calculate it. If you calculate it, by the way, in Desmos or in your graphing calculator, you should get 9 pi over 8, or it's like 3.53 and change. Okay? That's what you should get. You'll know you got the answer right. All right. That's one way to do it. Now, there's multiple ways to do this. That's what I want you to understand. You could also do this. The integral from pi over 2 to pi of 3 sine 2 theta squared d theta. Because pi over 2 is here, pi is here. That would find you the area of that one petal. Okay? You could take 1/2 the integral from negative pi over 2 to 0 of 3 sine 2 theta squared d theta. Negative pi over 2 is down here, 0's over here. That would find you the area of that petal. Okay? You could go from pi to 3 pi over 2. Pi to 3 pi over 2 would find you the area of this petal. You could find the area from 0 to pi and then take half of it. Find the answer that you get by taking 1/2 the area, or the integral from 0 to pi, 3 sine 2 theta squared d theta, and then taking half of it. Because this to here are both of these petals, but you want the area of only one of them. Okay, so that's what I want you to understand, is that a lot of these problems, there are multiple ways to do them. All right, and you should understand, look, the biggest thing that's important is when you find the angles that you're looking at and draw these radial lines, you need to cover the entire area that you want to calculate. And make sure that alpha is smaller than beta. So for example, if I wanted to say, let's say I wanted to take 1/2 the integral from 3 pi over 2 to 0 of r squared d theta. That doesn't work because 3 pi over 2 is smaller than 0. Okay? That integral cannot be written like that. Remember, the lower bound cannot be smaller than the upper bound. All right? And then understand that if you were to negate it and just switch the bounds, now you have something totally different. So if you were to negate this integral and switch the bounds, you'd be integrating 0 to 3 pi over 2. Well, that's not the area of one petal anymore. That's from 0 all the way over to 3 pi over 2. That's the area of 3 petals. Okay? So that's what I need you to understand. All right? So you have to be very careful with the angles that you write down. They need to be written in the correct order. All right? And you need to know exactly what area you're finding, okay, and need to calculate. All right, finally, let's find the area of the polar curve r equals 1 plus sine theta cosine 2 theta on the interval from 0 to pi over 2. Now, I put this problem here for a reason. To be honest with you, this problem is actually fairly easy to find the area. To find the area, I'm giving you the angles to work with. So that's not the difficult part. It's just going to be 1/2 the integral from 0 to pi over 2, 1 plus sine theta cosine 2 theta squared d theta. That's all you're going to have to do. Now, what I put this here for was because I do want you to understand that you do have to be careful about what it is that you're writing down. Okay? So, for example, you can see that there's a point here at 1, and there's also a value here at 0. So what a lot of people do is they naturally assume that, oh, well, this point must be 0, 0. That is not necessarily the case. So, for example, if I were to substitute 0 in for theta, I get r equals 1 plus sine of 0 cosine of 2 times 0. Whoops, not 2 theta, 2 times 0. So that's 1 plus sine of 0 is 0. Cosine of 0 is 1. So r is equal to 1. So the angle theta equals 0 corresponds to this point out here. Okay? This is the point 1 comma 0. Now, 0 is actually where theta is equal to pi over 2. Because if I plug in pi over 2 for theta, I get sine pi over 2 times cosine of 2 times pi over 2. So that's 1 plus 1 times 2 times pi over 2 is pi. Cosine of pi is negative 1. But 1 minus 1 is 0. So this point here at the polar axis, or the pole, is the point 0 comma pi over 2. So that's what I need you to understand. Just because you see a point at 0 at the origin does not mean that 0 is the angle that gave you this value. You have to be very careful here because, again, there's other angles here that also could potentially give you 0 as an R value. So you do have to be very careful. Okay, this is how I would find the area. And again, you're going to see more of this in the next video when we start to take multiple areas or multiple functions and put them on the same graph. As always, thanks for clicking.